Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering. Okay, let us continue our discussion on the atomic basis of elastic behavior. What we have seen yesterday is we have gone through some of the elastic behavior of crystalline materials in tension as well as compression mode, right? What we have seen is something yeah, this is the kind of stress strain behavior we have seen, and then we have come to a conclusion that the stress strain ratio is high because the applied stress works in opposition to restoring force of primary bonds, for example ionic covalent metallic bonds. Similarly, we also started our discussion on the non-crystalline materials such as glass, cross-linked polymers may also exhibit linear elasticity, for their structure is such that distortion is opposed from the start by primary bonds. Okay. Yeah. So again, we looked at the typical elastic behavior of elastomers, and we have seen that the first physical activity in this tension is stretching of chains in first activity is alignment in the direction of tension force, and then further elastic elongation requires stretching of the chains in opposition to primary bonding forces. And we have also seen that there is a significant difference between elastic response in tension versus compression in this class of material, and that we have attributed that to the compressive stress applied to the elastomers initially causes a more efficient filling of space, and then the moment the space available for filling, then the resistance for the compression increases significantly. That is the reason why you see the significant increase in the slope initially as compared to tension forces here. So this is what we have seen. We stopped here and then we ended our lecture yesterday. So we will continue this our discussion in this direction. Now I will show the other type of elastic deformation behavior, and what you can see is it is exactly it appears exactly opposite to what we have just seen yesterday, right. So you see this elastic response in a tension domain, like tensile force is much steeper as compared to in a compression mode, right. So very interesting behavior. So what kind of material will exhibit this kind of behavior? So we are now going to talk about elastic behavior in a compression and tension of cellular materials that exhibit elastic buckling of cell walls under compression. So the other class of material is cellular materials. Okay. What are cellular materials? The name itself has some answer. The structure is made up of cells. The microstructure of these kind of materials made up of cells. There are a lot of examples. Even natural material wood is also considered a cellular material. So you have lot of cells. The cells could be open cells or it could be closed cells. It could be vacuum inside the cell or it could be some gas filled, depending upon what we do in the processing procedure, right. So we will just talk about those kind of material. So the one example, classical example is the natural wood may be fairly stiff in compression until the stress is sufficient to cause elastic buckling of cell walls, at which point considerable strain may accumulate without much increase in stress. Okay. So what is shown here is we are talking about fairly stiff in compression until the stress is sufficient to cause elastic buckling of cell wall. So, we are talking about not primary bonds like in the other materials, we are talking about the buckling of cell walls. I said the microstructure consists of cells. So, the cell wall, elastic deformation of the cell wall, that is called buckling, is considered the energy absorbing event here. So, once the cell become, cells start becoming or cells start to buckle, then it also try to get compacted. The stiffness may then increase again as the cells become compacted. Okay. And considerable nonlinear strains may be recoverable in such substances. Of course, if the stress becomes high enough, the cell walls will crush and the strain may not then be recovered. So, that is also possible. But most of the, you would have seen that damping materials, right? These cellular materials are used for damping applications. So, that means it can take lot of strain which may be recoverable, large amount of strain, considerable nonlinear strains can be recoverable from such substances beyond, up to certain point till the cells will start crushing. In tension, clearly the cell walls do not buckle elastically in the same way as the typical stress strain curve is shown in figure. So, this is the reason why it looks, the energy absorbed in the elastic region is considerably small because of the buckling mechanism is not operational in the tension mode. So, the cell walls do not buckle elastically, so it will be difficult. Okay, coming back to our Condon-Morse curve again, once again, just to give a completion of thermal effects. So, we just talked about elastic response by stress as well as temperature, we said, right. In order to change the shape or volume of a material, initially we said that there are two things which we can do. Either we can load the material or apply the stress or change the temperature. These two things can bring some change in shape and volume of the material. So, we have seen this diagram already. Just to complete our elastic property also, we need to bring this aspect because temperature also plays a significant role. So, what is shown here? Potential energy versus distance diagram, and this you are now very much familiar, that is D naught is in equilibrium position, and if you start increasing the temperature, and of course this equilibrium position D naught is valid at 0 Kelvin, and as you move from 0 Kelvin to higher temperatures, then the material will tend to oscillate between these two positions, okay, the A and B. The atoms will try to oscillate, and as the temperature increases, then the oscillation distance also increases, right. This is what we have seen. Yeah, this is what we have seen already. So, clearly because of the asymmetry of potential energy curve, so this is asymmetric nature, the mean spacing will increase with increasing temperature. This aspect also we have already seen, just for completion here I am giving it here. The linear thermal expansion resulting from the temperature increase dt may be expressed as dl by L is equal to alpha dt. See, where alpha is thermal expansion coefficient and L is the length at which the given temperature, dl is the change in length resulting from the temperature change dt. Okay. This also we have seen. So, now getting into the again physical properties because of this temperature response, the sublimation temperature of material and its thermal expansion behavior and its Young's modulus all depend on the strength of bonds in the material. So, we were just relating the bond strength with elastic constants, right, earlier stiffness and all we have just seen. Now, we are also seeing that sublimation temperature of a material is also connected to the strength of the material. So, it may be seen from the figure that when a Condon-Morse potential energy trough is very deep, okay, we are now talking about, yeah, this diagram is interesting diagram, you can see that. So, the Condon-Morse curve is of different nature here. So, this is for what is written here, it is written strong, that means very deep. So, the trough is very deep. Then what it means, it is as it for covalently ionically bonded solid and some metals of high sublimation temperature. So, materials with stronger bonds, ionic, covalent or high melting point materials, their Condon-Morse curve will have a deep, very deep trough like this. Okay. So, similarly, the coefficient of thermal expansion is small and the energy necessary to cause the sublimation large and Young's modulus is high. So, these are the characteristic of when you have this potential well diagram is by just looking at the potential well diagram, you will be able to relate these two, thermal expansion coefficient, energy required to cause sublimation and Young's modulus. So, they will be very high for a material of this nature. So, if the potential energy trough is less deep for most solid with the metallic bonds and it is relatively shallow for those with the molecular bonds. So, see for the metallic bond we can relate this, for molecular bond like polymers this can be like this. Okay. So, such solids therefore expand, melt, sublime and deform under stress more easily. So, now we are now relating just by looking at potential energy curve, we are talking about deformation. So, this is the idea for which we have been discussing all this these days. So, when you have the a shallow potential energy trough, then the material can easily melt, it can easily sublimate or it undergo sublimation or it can undergo deformation with more easily. So, this is very important point, right, you have to keep in mind. So, the sublimation temperature is directly related to the depth of the trough. Young's modulus is inversely related to the radius of the curvature at the bottom of the trough, and thermal expansion behavior is related to the degree of symmetry of the curve. So, these are the additional points. We have some general remarks whatever we have seen, whether it is a deep, shallow or weak and so on, and further you can relate this symmetry of this curve to sublimation temperature, Young's modulus and thermal expansion behavior through these 3 points. So, what we are seeing here is the important message what we are trying to give from this discussion is the bonding nature has a strong connection to its mechanical behavior, whether it is elastic or plastic and so on. Okay. Right now, we are discussing elastic deformation, we will also see the plastic deformation in due course. So, next fundamental aspect I want to discuss is a term called anelasticity. Anelasticity, very important phenomenon. We all know this terminology, but we may be just looking at the behavior directly in a day-to-day life, or and we may not be realizing that what is happening to this material and so on. And this is this section of this lecture will be little descriptive, but conceptually it is very important. So, I want to mention that we will just discuss a bit slowly so that you will not miss any important points. Okay. The migration of atoms, defects and thermal energy. We are talking about migration of atoms, defects, thermal energy or time dependent processes. This can result in a lag of strain behind stress. The dependence of elastic strain on time as well as stress is known as anelastic effect. So, we are throwing a lot of terms here. Each term is very tricky and important also. Okay. So, we are talking about time dependent processes, migration of atoms, defects, thermal energy and so on. This can result in a lag of strain behind stress. So, what does it mean? Okay, you may apply a stress rapidly. You will not see the strain effect immediately. Okay, it may happen. The strain effect will come as a time pass by. That is the meaning of the lag of strain behind the stress. Right. You may do certain activity, loading, unloading, right, heating, cooling. We can do all these activities in a much higher rate. Okay. So, all these activities supposed to create some strain in the material, but the strain is not happening immediately. It is not happening immediately. Then we say that, or if the strain happens, or the strain experienced by the material you can observe as a function of time, then we say that the lag of strain behind the stress. So, that is the meaning of this. So, we are now going to discuss lot of physical events which may know it already, but we would not have connected to this concept quite often. And we are going to look at all those physical events and then connect this with anelastic property. Okay. So, the definition is the dependence of elastic strain on time as well as the stress is known as anelastic effect. So, we are going to look at some physical event of anelastic effect. The material subjected to cyclic stress, the anelastic effect causes internal damping. Okay. What is this internal damping? A decay in amplitude of vibration and therefore a dissipation of energy. Vibrational energy in actual structures is damped out internally in this fashion and externally through joint friction, wind resistance, etc., etc. So, we are now trying to give some direct physical events for this thermoelastic effect. Okay. So, one of them is like one of the consequence, I would say, is the internal damping behavior. So, you all know what is damping, right? Just now we have just discussed about the cellular material, which is also being used for the damping. No, that means what? It absorbs a lot of energy, right? So, what it means? So, it takes load in a very high strain rate. It can take quite recoverable elastic strain, but then it can also relax as a function of time. Okay. So, this is very important. We will also see the parameter a little later, something called relaxation times, right. So, this is a very important aspect to focus on. Okay. So, that is internal damping, the decay in amplitude of vibration and therefore the dissipation of energy. So, this also we will see now, and these are all vibrational energy in actual structures is damped out internally in this fashion and then externally through joint friction, wind resistance and so on. Okay. So, the term anelasticity is applied to stress and time dependence of elastic strain. So, time dependence of elastic strain is anelasticity. Okay. We will be using this terminology later in plastic deformation also, like we will be using this again the same concept in when we discuss high temperature deformation behavior called creep and so on, right. So, this is a fundamental starting point. The asymptotic approach of elastic strain to its equilibrium value with the passage of time after application of load is known as elastic after effect. So, there are different terminology people have given, but the physical event is the same. Okay. What is the physical event? Asymptotic approach of elastic strain. That means what? The strain will start slowly coming down and it will never touch the zero. It will just go parallel to the lowest possible. It will try to go and these two curves will never meet. It will meet in the infinity. It will go towards infinity. Very slowly it will come down. So, that is asymptotic approach of elastic strain to its equilibrium value with the passage of time. Okay. So, that is important. For example, in structures subjected to cyclic loading or to vibration, the lag of strain behind stress causes dissipation of energy or damping. So, this is what I just said. This very simple example is damping, vibration damping, or it could be any other damping as well, right. But it is more easy to realize when the structure is subjected to cyclic loading. Vibration is also yes, kind of a cyclic, right. It is not just constant amplitude vibration. It will go with some particular frequency, right. So, the energy may also be dissipated during isothermal monotonic loading by plastic or non-recoverable deformation. This phenomenon is known as creep. I just mentioned, right. We will look at this plastic deformation, high temperature plastic deformation. This also involves a non-recoverable deformation. That also can happen as a function of time. So, first we will see some basic physics behind this thermoelastic effect. There exists an interrelationship between the mechanical work done on the material in the elastic range. Please understand, we are now talking about only elastic property. Don't think that we are talking about plastic property. We are still talking about elastic properties, and all this load stress we are talking about still in elastic region. So, the material is in elastic range and changes in its thermodynamic properties. What are thermodynamic properties? Here we know, right, lot of thermodynamic properties, enthalpy, free energy, temperature, entropy and so on. Okay. So, the relationship here, what are the interrelationship here we are talking about? Between stress and strain, that is mechanical work parameter. On the other hand, temperature and entropy of the material. This relationship is known as thermoelastic effect. So, the interrelationship between mechanical work and thermodynamic properties. Here it is a stress and strain and temperature and entropy. So, how do they relate? Suppose that an elastic stress is applied to a rod so rapidly that the maximum stress is reached before the rod can exchange any thermal energy with its surroundings. So, this is exactly we are discussing about, right. Rapid loading, then what happens to the material? Okay. So, in this case, the elastic stress is applied to a rod so rapidly that the maximum stress is reached before the rod can exchange any thermal energy with its surroundings. Then what happens? The heat transferred to and from the rod is 0. So, the change in internal energy is caused only by the mechanical work done on the material, and the stressing is isentropic. Okay. So, it may then be shown that for uniaxial adiabatic straining, because there is no thermal exchange, it is considered adiabatic straining, then it can be written as dou T by dou epsilon at constant S is equal to minus Vm alpha Et divided by Cv. Most of the parameters you know. Dou T by dou epsilon at constant entropy represents the change in temperature with respect to strain at constant entropy. Vm is the molar volume of the material, E is the isothermal Young's modulus, alpha is coefficient of linear thermal expansion, T is absolute temperature, and Cv is the specific heat at constant volume. Okay. So, this is the relation for thermoelastic effect. Virtually all materials exhibit a volume expansion on heating. This we all know, right? All materials in general exhibit volume expansion on heating, but certain material gives opposite. You should just guess, or you would have seen this already. Since alpha is almost always positive, therefore V, T, E and Cv are also positive. It may be seen that adiabatic elastic tension lowers the temperature of the material and adiabatic elastic compression raises it. Okay. So, these are some of the salient features we have to note down. Then we will just look at some examples. The temperature what we discuss here is temperature change is usually small. You should not think that it's a huge. Okay. The temperature effect which we talk about in all this is small. So, the behavior of stretched rubber provides an interesting contrast to the general behavior just discussed in that alpha. The coefficient of linear expansion is negative. Therefore, rubber heats up on rapid stretching and cools down on rapid compression. So, this is something contradict to what we just said. We said in general most of the material tend to expand on heating, but there are exceptions. So, here we see that the stretched rubber, okay, the moment you stretch the rubber, the linear expansion, thermal expansion is negative. What could be the reason? The reason for a different sign of alpha is that with increasing temperature, the vibration and bending of the molecular chains of which the rubber is composed of increase to such an extent that the mean chain length decreases, and that is the rubber shrinks. Okay. So, we have looked at some of these basic molecular chain in the previous classes. So, the vibration and bending of the molecular chains causes a mean chain length, a decrease in the mean chain length. So, which attributes to the shrinkage of this rubber while heating. So, that is one observation why it is giving negative behavior. Okay, now what I am going to do is we are going to talk about this thermoelastic effect in a much more realistic manner, and for that I am just going to describe the two types of stress strain behavior. And what is shown here is sigma versus epsilon, and you just assume that any crystalline material is now being warmed up or stretched, right. So, when it is stretched, it is supposed to warm up, that is the general behavior, right. So, you just think such kind of a situation when the material is stretched. There are two kind of stretching is possible, like as I said, a very slow stretching, that means also equilibrium stretching, you can say that, or we can do it very fast, okay, like we described certain events before, right? We can do it very rapidly. So, what you can see here is there are two situations here: adiabatic straining or isothermal straining. Okay. Suppose if I am straining a material slowly, okay, so there is no problem with any thermodynamic aspects. This is called isothermal, okay, straining. Okay. On the other hand, if I stretch it very fast, rapidly, and I am not going to get the final strain which I am supposed to reach, EI here. Instead, I land up in EA. Okay, instead of EI, this is my original elastic strain if I stretch it slowly, and if I stretch it abruptly, then I reach a point A where I get only EA of the strain. So, that means there is no temperature exchange with its surroundings. So, this is adiabatic process, and then if I allow that material to relax, okay, and then it warms up and then it relaxes to the strain EI. So, that is one way of looking at it. Okay. Similarly, instead of unloading slowly, which is also again will pass through this line, I do it abruptly here. Then again it is exactly the opposite, things will happen, thermodynamic properties, temperature exchange and so on. It will not go to 0, or that means it will not recover all the strain. Instead it will go to A dash. As the time pass by, it will just slowly reaches its original or equilibrium strain. Okay. So, this kind of a cyclic loading or cyclic event like stretching, unstretching or stretching, relaxation involves some energy dissipation. So, that is the energy shown here. So, it is called hysteresis, elastic hysteresis loop. The hashed region here is the amount of energy involved in this process, whatever I just shown. This is in a hypothetical situation, but what is shown here is an actual energy per cycle. Okay. 0 to 0 OBX, 0 BX or 0, this again it can be I also, you can put I. So, 0 BI and then ICO cycle. So, it could be either isothermal cycling or adiabatic cycling. So, that is the idea. So, with this background, we will now look at some other details. The stress strain curve of a sample loaded and unloaded in a continuous cycle would resemble the loop OBICO shown in the figure instead of a parallelogram OAI A-O. Okay.